Okay. All right. This is the last lesson before we have our test, and that test is come quite quickly. Like I said, this was a very short, predominantly review, right? So again, whether we have a test on Friday, it's not going to be that big of a deal, but it is still a test. All right. Just as a point of clarification, I have some musicians in the afternoon class that have to miss the test, and we've accommodated them. Are there any musicians in this class that will be missing my test? No? No? Excellent. Good. Good. All right. But we do have French immersion students. Is that correct? And we've got about 5 of those French immersion people. And there's no way. Can I get you to write it tomorrow? I'm getting the musicians to write it tomorrow. If you're wanting to write it tomorrow because maybe it's fresh in your mind and that type of scenario, you see they're coming during the music class, but I would have you write it during the explosions. You probably want to see it. I really don't care. If you really want to write it tomorrow, instead of watching me blow things up, then you can let me know if that's the case. You want to get it out of the way, fresh in your mind, that type of thing. Yeah, let me know by the end of class, and I can easily have you write it tomorrow if you want to do that. And if you don't, you can write it on the Monday at lunch, just like we had planned. So still, that's fine. Okay, I just wanted to get that clear, make sure that I didn't have any musicians I had to accommodate for as well. Okay, so we talked about balancing right at the beginning. We talked about different types of chemical reactions. The first day, combustion, synthesis, decomposition. We then did a lesson on single displacement. I introduced to you the activity series. The ones at the bottom want to be alone. I then did double displacement, and I introduced to you the solubility table. And if it is a solid on the solubility table, it will form a precipitate. We also talked about neutralization reactions, which acid and base form a water and a salt. And we talked about a couple of reactions that produce gases. This lesson here goes kind of back. This lesson usually comes at the very beginning of the lesson or of the unit, but sometimes if the timing doesn't work, I put it at the end. You guys have talked about chemical reactions in the past, grade 9 and 10, so we can still go through the different types of chemical reactions without you having to worry about this and without it being at the beginning. So this is almost like a summary of why chemicals react, and again, a summary of that list of how we know whether a chemical reaction has taken place. But again, we've talked about that. So essentially, I want to talk to you today about 2 theories that kind of work together that result in chemical reactions. And one is called the kinetic molecular theory, and that's something you've talked about in the past. Even in elementary school, I'm very sure that you probably did a unit on heat and on motion of particles. You might have talked about conducting heat, conduction. You might have talked about convection, all right? You might have talked about radiation, different ways in which heat can be moved. The kinetic molecular theory is that theory that doesn't explain chemical reactions, but explains the way atomic-sized particles behave when they're heated. All right, it's that simple. It's really a heat theory, an explanation of heat. So that's what the kinetic molecular theory is. Collision reaction theory is a theory that goes on the assumption of if a chemical reaction is going to take place, a collision between the reactant molecules must occur. There must be some kind of interaction between those 2 reactant molecules, all right? And the kinetic molecular theory, along with collision reaction theory together, can therefore then explain why and how chemical reactions take place. This is a very preliminary introduction to this theory. Again, in grade 12, we go into far more detail in explaining things using this particular theory. So this is really just an introduction. Okay. So let's start with our discussion first, and I'm going to bring everything up so you can write it. First, I want to talk about physical change versus chemical change. We're not going to go into great detail on this, all right? Again, stuff that you would have done in elementary school, you would have been introduced to it. Grade 9, they would have talked about physical change versus chemical change. You would have talked about physical properties versus chemical properties, almost ad nauseum, on and on and on. It always invokes discussions very similar to the orange juice with pulp discussion. Remember that at the beginning of class? Does it have pulp? Right? Homogeneous versus heterogeneous. Same discussion takes place here, physical change versus chemical change. Chemical change not easily reversed. Well, it doesn't have to be drawn just like that, but all I'm saying is I'm just reminding you of the terminology of the changes of state. So you don't have to have the diagram. You could just have the word solid, liquid, gas, vaporization, solidification, et cetera, or sublimation. But that discussion on physical versus chemical change, the classic discussion, toasting toast. That's a chemical change. Not easily reversible. You could scrape it off, something like that. No, that still doesn't count. Anyway, frustrating times. But I'm not worried about that here. I'm going to assume that you know that during a physical change, that the substance isn't actually changing into a new substance. It's just changing its form or its appearance. So when ice melts, you have H2O molecules that are in the solid state becoming H2O molecules that are able to move past each other in the liquid state. And you guys know that. You've heard that over and over again. Dissolving is also considered to be a physical change. So when something like sodium chloride in its ionic lattice structure is put into water, and the sodiums and the chlorides go on their way, it's still sodium ions and chloride ions. It's just in a different orientation. Instead of being in a nice lattice structure, when you dissolve it, the sodium ions are able to go free, the chloride ions are able to go free. They're mobile ions, and therefore it's still sodium chloride ions. That's a physical change. Melting, vaporization, condensation, freezing. There is a term that's often used. I'm not going to have you write it down here, but sometimes they'll call the freezing melting, they'll just call it fusion and have it be both of them. So fusion going one way and fusion going the other way. It's not like nuclear fusion, but it's a term that they use. You'll be introduced to that next year. It's not a big deal. Okay, so physical change. Changes its appearance, but essentially the same stuff. Versus a chemical change. A change in which a new substance with different physical and chemical properties are formed from the starting materials. That's going to lead us to our evidence of chemical change. Typically, physical changes are low energy changes. Doesn't take much energy. Well, I got to watch that. Well, no, that is a true statement. But if I want to melt ice, I just need to put it in the palm of my hand. But I guess if I want to melt something like gold, that's not going to work. I need like 3,000 degrees. On average, physical changes are lower energy reactions than chemical changes. But that's not to say that that's true in every case. You can have a fairly low energy chemical change, rusting of iron, even if you were to combust it, fairly low energy involved in that. And then obviously melting of some metals, a lot of energy. Tungsten has the highest melting point, 5,000 degrees. But on average, physical changes are low energy interactions, with chemical changes being a medium energy interaction. Okay. We good to go? All right. Yeah, Atlee's playing with his page. He is ready to go. Evidence for chemical change, so I'll bring it all up here. I knew there was 5, but we put temperature, heat, or light. I think when we were discussing it, we put it together as 1, right? Which is where that 5th one was. Change in temperature. Couple of terms there. You may have encountered them before. Have you heard of the terms exothermic, endothermic? Yep, all right. Exo, to exit, to leave. Thermic, from thermos, not like from the thermos you put your soup in, but it's a Greek term, thermos, meaning heat. So exothermic means that the thing that is reacting is giving heat off. Combustion reactions are exothermic. They give a lot of heat energy off. If you have those little packets that you put in your gloves, say when you're skiing, you know what I'm talking about. You open them up, you shake them up. 2 chemicals in there. When you shake them up, you're allowing the chemicals to mix. It's an exothermic situation. It gives heat off to the surroundings, your hand. Endothermic absorbs heat. If you've ever injured or been injured playing sports, usually the trainer has one of those little white packs. You mix the 2 chemicals together. That absorbs heat. It's cold, so heat's being drawn into that chemical reaction. It's an endothermic situation. Change in color. We saw lots of that on our lab yesterday. Formation of a gas. We saw some bubbles. Formation of a precipitate. We know what that is. And production of light. We didn't have any light-producing chemical reactions, but if you have ever, had one of those glow sticks or one of those necklace things, you know what I mean, where you break the little glass on the inside, 2 separate chemicals in there. When they come together, they produce a chemical reaction, produces light. You would have probably talked about that a little bit in your optics unit last year. All right? Nothing earth-shattering there. And again, even though we didn't review this at the beginning of this unit, I don't believe your educational experience was diminished in any way. I think we all kind of knew these. We just hadn't written them down officially. Okay, so why do these changes occur? 2 theories account for the changes. You're all writing like crazy, but you know what? That's really stating what the title page stated. So if you didn't write it down, you're probably not gaining anything great there, because my next slide is going to be the kinetic molecular theory, but some of you guys have already darted across and started to write. Finish it off if you'd like. But again, that's not really an important slide. So for those who are writing in pen, they're going to keep going. Pencil writers are stopped at this point. And Dallas is firmly into the note. You done? All right. So let's talk about then the kinetic molecular theory. Now again, you've probably learned this before. Now sometimes it's written down with a series of rules as proposed by the kinetic molecular theory. Essentially, it states that all matter is made up of particles in continuous random motion. Again, I don't believe anything new is being taught here. the more energy the particles have, the faster they move. And to go along with that second bullet, temperature is actually a measure of the speed in which they move at. The higher the temperature, the higher the average speed. We write down information about tiny little particles and the way they move, and we don't even think twice about it. Again, I'm assuming you've actually heard this stuff before, and this isn't any surprise in any way. But like even 100 years ago, even just 100 years ago, early 19th century, it was just turning out that there was evidence for this. If we go back 200 years ago, that brings us back to about Dalton's time, right, 1820 or so. And Dalton is proposing the atom, right? Remember that way at the beginning we talked about Dalton? His were the billiard ball atoms, didn't have any features, no protons, neutrons, electrons, just little pieces. And that was really kind of the beginning of this kinetic molecular theory. Many scientists really didn't believe in atoms, not even until the late 1800s. You can do chemistry, you can explain lots of chemistry without even thinking about an atom. It just means you don't think about molecules as being individual pieces, but you think about something like H2O as being a ratio of masses or a ratio of substances, all right? So you get H2O and you have this ratio of stuff, and it's not even necessarily atoms. So if you think of it as just being a ratio of masses, and it turns out that it's always that same ratio, then you don't need atoms in order to explain chemistry. You can explain a lot of chemistry without atoms. So Dalton proposes atoms, and now they kind of go, whoa, this really makes good sense now, because now it's not just a ratio of masses, but it's a ratio of these little things called atoms. Now, unfortunately, in science, and this is the same in any particular career that you are going to find yourself in the future, you're going to find that there's the old guys, or girls, don't want to be sexist. And the old people that are still working on the verge of retirement are going to have a particular view of the way to do things, and you're going to be that young punk. Sorry, did that come out that way? Am I that old guy now? Maybe I am. You're going to be that young trend, groundbreaking, and all the old guys are going to be, oh, you young guys, you think you're so smart. And the old guys are going to just keep doing it the way they used to do that. I'm going to still do it this way. I don't really care. All right? That's the same with science. Science is very much that way. All the old guys, Dalton, some young kid coming along proposing atoms, they're saying, what? Atoms? That's the craziest thing I've ever heard. I've been doing chemistry all my life. I can explain things. I don't need these atoms. And so it took about 100 years for scientists to kind of get into this new idea of atoms, all right? There was a couple of scientists in the mid-1800s, so we're talking about 30 years later. One by the name of Maxwell, the other one by the name of Boltzmann. One guy was German, the other guy was English. It doesn't make any difference. And they were mathematicians and scientists. They tried to build a theory to mathematically study or explain each individual atom and what it would do if it was moving. So they started with a very basic premise. Let's take an atom proposed by Dalton, which some don't believe, and let's start doing some math on it. Let's assume some speed, v, some mass, m, and to all you physicists, this is really starting to sound like a really big physics problem. Let's calculate some kinetic energy, and let's calculate some momentum, and let's now then take that one particle and put it in a sample of n particles, which could be millions and millions and millions, but let's just call it n. And let's start doing mathematics on this. They did something called statistical mathematics, where instead of dealing with one particle, they mathematically dealt with this theoretical group of n particles. And as they carried the math through, it turned out that they came up with an equation that then could measure this average kinetic energy or the average speed of these particles. And when they did that, they resulted in a value or a variable. I don't know what they called the variable, but in the end, that variable was equal to the temperature. In other words, they mathematically concluded that the speed of the particles is directly related to temperature. You have a higher temperature, theoretically, you have faster moving particles. You have a lower temperature, theoretically, you have slower moving particles. All right? This theory, this mathematical theory, was not only able to predict temperature, but to predict pressure, another very important feature of gases, and predict all kinds of other different features. Even though these guys did all kinds of math to explain particles, still the old guys, no, that's crazy. So what if the math works out? We still have never seen particles moving. They're too small to see, so if you can't see them, how can you assume that they exist? We need some evidence that they exist. It wasn't until 1905, there was a scientist in the late 1800s, a guy by the name of Brown, don't know his first name, but he was looking at, and I don't know why, smoke under a microscope. I have no idea. I don't think smoking was prevalent in the late 1800s, not as prevalent as in the mid-1900s after like the wars where everybody was smoking, right? But maybe he was smoking and looking at his microscope. Who knows? He was looking at smoke under the microscope. And he noticed that under the microscope he could see individual smoke particles. And these individual smoke particles didn't just sit still, but they jumped around, just randomly. They didn't actually get pushed around in any particular way, they just jumped around in place, just wiggled back and forth in place. It's called Brownian motion because he was the first one to see it. Albert Einstein did some mathematics, took the numbers that Maxwell and Boltzmann took, and applied those numbers to what it would do to a smoke particle. Took the math of the invisible gas particles in the air, the way they're wiggling and jiggling, applied it to the visible smoke particles, and the predicted theoretical movement of the particles by Albert Einstein was exactly perfect to what Brownian saw. So now you've got visual evidence, moving smoke particles, mathematical link to it, Albert Einstein doing the math to predict what the particles should look like when they move, perfect. Finally, the old guys. All right, there might be atoms. Okay, I believe you. Took about 100 years for the idea of atoms to come into play and for the idea of this kinetic molecular theory to come into play. Okay, so let's talk a little more about what this kinetic molecular theory does. Oh, I'm backing up. Kinetic molecular theory essentially accounts for physical changes. Especially the change of state changes. Dissolving can be explained in another way as well. You could probably use the kinetic molecular theory to do that. You might be able to explain why something dissolves better at higher temperatures. As the temperature increases, the particles in a solid move faster until they have enough energy to become a liquid. Now, this is a really very quick statement here. The particles themselves don't become liquids. I hope we're all aware of that. But the particles get so much energy that they move so quickly and break out of their lattice structure. A classroom is a great example of an analogy of a solid. Right now, you are sitting in nice rows and you are behaving as a solid. I think I used this analogy earlier on this year. Did I do that? Maybe not. in my classroom here with you guys sitting nicely in rows, you are simulating a solid. You don't have a lot of movement. Some of you are moving back and forth. Some of you, get very nervous, moving your legs up and down there. Others falling asleep, right? Head bobbing going on as I talk away, right? All that good stuff is happening. So there's a little bit of motion, but not a lot. You're locked into your seats. And that's the way a solid exists. The particles are locked into their place. Whether I'm talking about an ionic solid or even ice, like a molecular solid, doesn't matter. There's particles locked into place. Now, a liquid is when you have the particles able to break out of that position and be able to move freely past each other, all right? So let's think of increasing the energy of this class. Not actually going to do it. That would be crazy. That would be like too much fun. We don't want to have too much fun. But let's imagine that I said, okay, let's now simulate a liquid. We're going to get up because we're going to teach the kinesthetic learners, those that like to jump up and down, and we're going to simulate a liquid. And so I want you to get some energy, and we're going to go down to the gym, and we're going to run around the gym all randomly. And you're going to look at me and go, no, we're not doing that because you're too cool, which is fine. I understand that. But if we did that, you would break out of your seats, you'd get some energy, you'd start to move kind of randomly, you might move into the halls, and as you're moving in the halls, you're going to move past each other and kind of bump into each other, but you're not going to break away from each other. So as you're moving in the halls, it's almost like you're behaving as a liquid. Yes, Mr. Johnson, how can I assist you?
You made it fun.
Did I?
Yeah.
Illuminate me.
You said that we wouldn't simulate a liquid because we're too cool.
Oh, you're right. That is good stuff. Yeah, but if you're cool, it means you don't have a whole lot of motion, which means you'd be stuck in your solid state. I like that. Thank you for letting me know that one. That's great stuff. Okay, so as you move through the hall, we would move as kind of a group. We would stick together a little bit, but somebody might pass somebody. Somebody might slow down. You might go past somebody. That's the way a liquid exists. So if you give the solid particles enough energy to break the forces of attraction that hold them into place, then you then have a liquid. We can extend this. If you then extend it to, say, instead of us moving in the hall, the bell goes and it's lunch, and you guys get really excited, you get lots of energy. In other words, we've heated you way up, then you're going to go right out the front foyer doors, and you're going to just go in all directions. Some of you are going to head to the right, to the left, down the street this way. And that simulates essentially a gas, because now you're not even being linked together by the halls themselves, but you've got so much energy, you've been set free, and away you go. Now, nowhere in time during our little analogy, our little thought experiment here, did your actual being turn into something else. You're still the same particle you were. It's just the orientation of the particles, how they exist with respect to each other, and it's the way they move past each other, all right? So when I say, as the temperature increases, the particles in the solid get vibrating so fast that they can have enough energy to move freely past each other and become the liquid state. Now notice, in all of this discussion, nowhere have I described a chemical reaction. We're just talking about particles getting enough energy to break out of their solid lattice structure and move freely. Again, as the temperature of the liquid increases, the particles move faster until they have enough energy to become a gas. Again, the particles are not transforming into a gas. They're just given enough energy that they're able to break away from each other in the liquid state and go off as individuals in the gas state and move freely throughout whatever space that they're moving in. All right? Okay? So that's how KMT can explain physical changes. The hotter something gets, the more energy the particles have, the faster they move. And if they get enough energy, they can break out and become the next higher energy state. Now for collision reaction theory. It counts for chemical changes. Now, the reason collision reaction theory goes in hand with kinetic molecular theory is because in order to have particles collide, they have to be moving. And the faster you get them going, the more violent the collision is. And if you want to invoke chemical change, then you want a violent collision. You want something that's going to blow the molecules apart. A chemical change occurs when the valence shells of the reactants overlap and electrons are rearranged to form new bonds. So you need to get these atoms close enough together to have bonds broken, new overlap bonds formed. Now, not every collision leads to a chemical reaction. That's a good thing. Right now, right in front of us, there are billions and billions and billions and billions and billions and billions. Okay, you get the idea. There's a lot of particles in the air. There's nitrogen molecules, N2, about 80%. You've learned that before, I think. 80% of the air is nitrogen. Oxygen molecules, about 20%. Now that gets me to 100. Actually, it's 79 and about 20, right? So that's oxygen molecules. And then there's a little bit of carbon dioxide, a little bit of argon, a little bit of water vapor as everyone exhales and perspires a little bit. So there's a little bit of those little things. But there's all kinds of particles in the air. Oxygen especially. Oxygen's quite reactive. We know that if we put something combustible with oxygen, it's going to burn. In actual fact, our skin is combustible. We're not going to do an experiment where we're going to hack off a chunk of somebody's skin and burn it, but it would burn. Skin has fats in it, which is a lot like our hydrocarbons, and it would burn. So there's a lot of oxygen in the air, and there's a lot of combustible material on our skin, yet we're not bursting into flames, which is a good thing. And that means that even though there are collisions going on, because right now those oxygen particles are bouncing off of our foreheads, right? They're running into us. We're not combusting. So obviously, not all collisions result in a successful reaction. So what does involve a successful reaction? Two things. Two situations need to be fulfilled in order for a successful reaction to take place. I've already actually talked about number two, energy. The particles have to be going fast enough. I'm actually going to talk about the energy situation first. Like I said, we're not bursting into flames, yet we're covered with combustible material. Same thing with the gas. I'm not going to light this up right now. We'll do some demonstrations tomorrow, but I can let the gas enter the room. I'm not going to do that for a long time. That could be dangerous, but I can. A little bit of methane is coming out of there right now. And yet, that didn't burst into flames. So those collisions weren't successful. It means that the reactants, the oxygen colliding with the methane, CH4, they did collide. Smells like gas. But they didn't react. Not enough energy. The particles weren't going fast enough. What could I do to make them react? Yep. Heat them up, give them some energy, right? There's gas over here, I'm not doing that. But if I do that, then I cause the collisions, the particles in that flame go really fast because they're hot. Temperature is the same as the proportional to speed. They run into each other. They blow the molecules to pieces, oxygen molecules and methane, and they come together as carbon dioxide and water. They give off their own energy, which means the energy from one reaction feeds the next reaction, and the reaction just keeps going. The flame keeps on burning until that energy is taken away. So energy is one. The second one is orientation. And orientation is a tricky little thing. When it comes to combustion reactions, orientation isn't a factor. Because when you combust something, you absolutely destroy the molecules, and they come back together as new, you don't destroy them all. Yeah, you destroy the molecules. You get individual atoms, but then they come together as new molecules. But for many chemical reactions, there has to be a certain orientation the way they run into each other. Large biological molecules are very much like this. When you have a reaction to, I can't even think of a situation, if you want to change a protein molecule in a certain way, you need to have that collision run into the other protein molecule right in the right spot in order for the reaction to happen. That's why biological systems are very slow usually. Their chemical reactions are slow because they don't run into each other in the proper orientation. What do you call the thing in biology that speeds up a biological chemical reaction? What do you call that stuff? A catalyst or an enzyme. You heard the term enzymes before? Enzymes, you guys do biology, enzymes? An enzyme is, what do you use as the analogy to describe an enzyme? It's called is it a lock and key or a something and key mechanism? No? Did you describe it that way? Yes? No? They might have. I hope they did. Well, who knows? What they mean is what an enzyme essentially does is hold a molecule in position so that the place in which they want it to collide is exposed and a successful collision can take place. All right? A silly textbook that I was reading had an example, and this was actually a grade 12 university textbook, and they're like, have your students shake hands with each other and have them think about what it takes to have a successful handshake. And now I'm trying to envision you guys have unsuccessful handshakes. You know, I don't know. Right? Where a successful handshake would only be, one particular orientation, right? And I'm like, really? We're going to have them shake hands? That's what we're doing in grade 12 university? No, we're not doing that. Anyway, there's a silly example, though, of how orientation comes into play. Okay, so in order for a reaction to be successful, you need the proper orientation, and you need things going fast enough. All right, one little example. This is the last slide, and then I'm going to give you a couple of little homework questions on this, but then I'm going to give you the review, and then you're off and preparing for the test. Oh, I also have just a little review practice sheet. It's got different types of chemical reactions, got some balancing on it. It's something that was originally created for the college chemistry, and then I got a copy of it and thought, yeah, it's not a bad little review sheet as well. So not an assignment or nothing to be handed in, just something you can do to prepare for the test. You're welcome. Yes. One more. It's okay. Yep. Gasoline will only burn if it's a gas. Now, let me explain. Even though we call gasoline gas, gasoline is a liquid and not a gas. That was a fun little statement. Do you understand what I'm talking about? We need it to be vaporized. Technically, you could put a match out in liquid gasoline. Don't try that. Don't do that. You will fail. I shouldn't even be recording this. But technically, if you had the match and the cool liquid of the gasoline coated it, it would cool the match down and put it out. But in the process of attempting to submerge your match in gasoline, there's a whole bunch of vapor coming off of it, above it. As you approach that, you are now engulfed in flames. You may get there and put it out, but at a great cost. So don't do that. Liquid gasoline doesn't burn, but vaporized gasoline burns. Okay? Does that make sense? Don't try that. Jeepers. If you've ever tried burning diesel fuel, you should never have done this. I should not be recording this conversation. What happens when you try to burn diesel fuel? We live in a farming community. Sometimes you might use diesel fuel to burn something. If anybody attempted to light some diesel fuel on fire, it's okay. I'll keep it anonymous. Anybody try to light diesel fuel on fire? What's that? It doesn't work very well. Thank you. No, I'm not going to say who that was. It doesn't work very well. And that's because diesel fuel doesn't evaporate as quickly as gasoline. Have you ever spilled gasoline on your hand? Yes, no? Or if you've ever, painted with oil-based paint, you can actually use the gasoline to wash your hands off. It works. How does it feel on the surface of your skin when you get gasoline on the surface of your skin? It feels oily, but not for long, because it doesn't stay there for very long. What temperature does it feel like when you get gasoline on your skin? What's that? It's cold. It's cold. It's cold because it's evaporating quickly. That's what makes gasoline a great thing in an engine of a car, because you can have it as a liquid, but when you squirt it into the engine, it evaporates quickly. That's what makes it super dangerous. That's why you don't attempt what I told you not to attempt. If you've ever spilled diesel fuel on your hands, how does that feel? Less cold. That's the exact perfect answer. It feels oily, but it feels less cold because it doesn't evaporate as quickly. It's heavier, right? And therefore, it doesn't light as easier, right? You can't just take a match and light diesel fuel because it's not evaporating as fast. If you have a diesel truck or a diesel car, in the winter, what do you have to do to that car? Does anybody own a diesel engine vehicle? What do you have to do if it's really cold? What do you got to do? You got to plug it in or keep it warm. And that's because when it's really cold, the diesel won't even evaporate in the engine and it just won't run. So you got to warm the engine up itself so that the diesel can evaporate. So we need the fuels to be liquids to be gases in order to burn. So in the engine, because the engine is hot, the kinetic energy of the gasoline molecules, it warms it up, gets them all vibrating, turns them into a gas. That's the kinetic molecular theory. Once you introduce some oxygen to it, it still doesn't burn. Even though they're going faster and they're in the gas state, just like my gas coming out of the tap, still doesn't burn. But until you give it a little extra energy, then you can get the collisions to be enough to combust, and you then have a successful chemical reaction. So you need the kinetic molecular theory to explain vaporization, and the collision reaction theory to explain the actual engine burning. Engine burning, that's not a good thing. The fuel burning. A little bit of homework there on this note, and then my next slide has the review work questions. Yes. Yep.
Can you actually fire on a lighter and it will actually like?
That's exciting. We're recording this. Oh. That's good. That's good. The question was, can flatulence actually produce some burning? It would depend on whether the material in your gut produced methane or not. And the answer to that is yes. Some people produce more methane than others. Cows produce an excessive amount of methane, so you could try it with a cow, right? But the answer to your question is yes. However disgusting that might be, it's yes. It can. Anyway, all right. Excellent. That's collision reaction theory right there. So normally, your flatulence doesn't start on fire as you're just walking along. right? Mind your own business. But if you give it enough energy with your lighter, those collisions can become energetic enough to burn your butt. That's true. It's a true statement. That's a phenomenal question. Yeah. Someone's at the door. Excellent. Perfect. We even have visitors at this point. Jamie. There you go, buddy. Review questions. And I'm going to stop recording before we get more questions.